There are so many ways to move laterally and escalate privileges that as defenders, it's very likely we're going to be able to find them all in advance and stop attackers from abusing them. So we need a very effective way of figuring out how attackers are doing that once they get on our system. Without setting anything else up, let's take a look at the information that we can already get. So if the attacker used a shell like bash and they logged in as a user that has a home directory, we can check that user's bash history file. The bash history file has a list of all the commands that user ran. So if I go to, for example, we knew that as attackers, we logged in with with user hacker, right? So I can go to hacker's home directory by saying change directory home hacker. And then from there, if I print out the files that are here, you'll notice one called bash history. Of course, I need to be a root in order to actually be able to print out that file. You'll notice that user doesn't have the privileges to read hacker's bash history normally, but if I do sudo cat bash history, I can see the commands that the attacker ran. Here we can see that as an attacker, I cleared the screen, I ran that curl, then I ran wget to actually get that linp script, then I made that linp script executable, then I ran it, and then I exited. There are many problems and limitations of this way of logging what the attacker did. The first one is it relies on the attacker having used bash. If the attacker used any other kind of shell, like for example dash, then the command line history would not be logged. The second problem is that these commands are only logged after the attacker exits, not while they're actually running them. So if I started an SSH session as an attacker and then I tried as a defender to print out that history file, I would not be able to see what I did. So I can demonstrate that by logging in via SSH, and then I can ls pwd, and if I go back here and I try to print out that bash history again, you'll see none of that showed up in the bash history because it's only written to bash history after the shell is exited. So if I exit it here, and now I take a look at that bash history file, you'll notice we have that ls and pwd. The other problem is this method doesn't work for users that don't have a home directory by default. So let's say the attacker got in through some sort of web exploit. A lot of the times they're going to get in as the www data user, and that user doesn't have a home directory associated with it. So even if the attacker is using the bash shell, there's no history file that we can read to view the commands. The last reason that this is not a reliable method is that it's really easy to circumvent as an attacker. All I have to do is say unset hist file before I exit, and none of the commands that I entered as an attacker will be written to that bash history file. This is because the hist file environment variable is what defines where that history file is located. And by unsetting that hist file environment variable, bash is going to have no idea where to write that history to. I can demonstrate that by logging in, running some bogus commands that don't work, running some legitimate commands, and then saying unset hist file before exiting. And then if I, as a defender, try to print out bash history again, you'll notice nothing got printed out. So because of these limitations, we need another method of getting the commands the attacker ran without all of these limitations that are easy to circumvent. Going back to the GitHub repo that I referenced in previous videos, this time I want you to scroll down and under Linux Defense, take a look at auditing commands. This is a cheat sheet that I actually added just yesterday that talks about different methods to log all the commands that are executed by an attacker in Linux. I highly encourage checking out this blog post that inspired me to put this together. So looking at this blog post, it actually goes over a few different methods to audit commands in Linux. It talks about audit D, Snoopy, process accounting, and native solutions such as the trap method that I'm going to be showcasing in this video. You, of course, could run these commands as is, follow these instructions as is, and everything will be set up. But I want to make sure that you have full understanding of what each of these commands are doing and how this whole process actually works. In order to do that, first I'm going to go ahead and I'm going to introduce some new Linux concepts that we haven't talked about yet in the NCE Cyber Sandbox tutorials. Whenever we start a new terminal session in Linux, there are actually a couple of files that get run. The first one is profile, and the second one is bashrc. Profile is run whenever we log in. So for example, if I log out here and I log in as user abc123, the profile file gets run. In addition, if I were to switch users to a different user, again, I'm logging in, and therefore it's going to run the profile file. The second file that gets run every time I start a new terminal session is bashrc. This gets run whether I'm logging in or not. So for example, if I were to rerun bin bash, this doesn't require logging in again, so profile is not going to get run, but because I'm spawning a new terminal session, bashrc is still going to get run. If you're using a desktop environment, like on Kali Linux, for example, then bashrc is what actually gets run every time you start your terminal, because you're already logged in. But for example, if you're switching users in the terminal, you're logging in as a new user, it's going to run profile. So, in summary, profile gets run whenever you log in. Bashrc gets run whenever you start a new terminal session, whether that's opening a new terminal window, whether that's splitting your terminal screen, or whether that's rerunning bin bash. Where are these files actually located? Well, they're kind of located in two places. So you have the general system-wide profile and bashrc files that apply to every user, and those are located in etc. The profile file is usually called etc profile, whereas the bashrc file can be called one of two things. It can be etc bashrc, or it can be etc bash.bashrc. In Debian, for example, it's etc bash.bashrc. This profile and bashrc file apply to every user on the system. So whenever any user logs in, that profile file is going to get run, and whenever any user spawns a new terminal session, that bashrc file is going to get run. There are also per user versions of profile and bashrc, and those are located in the user's home directory. So if I go to my home directory, which I'm currently in my home directory, you can see if I print the current working directory, I'm in /home/user. If I list out the files here, you see along with bash history, which we looked at previously, we have this bashrc, and we have .profile. These only get run when this specific user logs in or spawns a new terminal session. So while the system-wide profile and bashrc run every time for every user, this .bashrc and .profile that are in the user's home directory only get run for that specific user. So if I were to log in as user, then users.profile is going to get run. And if I were to spawn a new instance of bin bash, or if I were to split the terminal or open a new terminal tab as user, then it's going to run users bashrc. I think this concept is best illustrated with an example. I went ahead and I added an echo statement to the beginning of each of these files, so that we'll know when they're being run. If I take a look at the .profile file, for example, in my user directory, I added this echo statement that says running/home/user/.profile. I'm going to go ahead and I'm going to log out, and then I'm going to log back in. You see that in this case, we have 4 files that were run. Etsy profile, or the profile file, was run because we logged in. The bashrc file was run because we spawned an interactive terminal session. It doesn't matter that we logged in and ran profile. Bashrc will run whenever we spawn an interactive terminal session, whether or not we're logging in. And because we logged in as user, both the system-wide profile and bashrc were run, along with the user-specific profile in bashrc. If I now spawn a new instance of bin bash, this is the equivalent of opening a new terminal tab. This time, profile does not get run because we're not logging in, but the system-wide bashrc was run and the user-specific bashrc was run. Hopefully, this example helps illustrate how profile and bashrc work and when they get run. The last point I want to make is that while profile is applicable all the time, bashrc is only applicable to the bash shell. In Kali Linux, for example, we're not actually using bash. By default, we're using Z shell or ZSH. I can see this by echoing out the environment variable shell, and you'll notice that this tells me that we're using user bin Z shell rather than bin bash. For other shells, like Z shell, they oftentimes also have the equivalent of a bashrc. In the case of Z shell, it's called ZSHRC. So if I list the files in my home directory here, we'll notice we have this ZSHRC in place of a bashrc. In addition, we have this Z profile instead of just a regular .profile. These function the same way as profile and bashrc. The only difference is they apply specifically to Z shell, which is the shell that we're using in Kali. What are these files typically used for? Well, profile is often used for defining environment variables. As a recap, environment variables are basically just variables or pieces of information that you can change that somehow influence how your terminal session behaves. So if I look at my environment variables with the env command, you'll see every environment variable actually has a key or variable name and a value. And I can print out these environment variables by saying echo and prefixing the variable name with a $sign. So if I want to print out my path, I can say echo path, and then that'll print out the actual value of that path environment variable. Now these environment variables get passed to child processes as long as they're run by the same user. What does that mean? That means that once we log in as user, if we were to spawn a new instance of bin bash, or if we were to split our terminal, or if we were to open a new terminal tab, or just open a new terminal session, the same environment variables will get passed on to each of those. And that's why we define environment variables. If we want to make changes to these environment variables, we would make them in profile. If we want to create, for example, functions or command aliases, we would do that in bashrc. Let's say I'm getting really tired of typing in some long command. Like, for example, let's say you're getting tired of typing in nmap-sc-v-t4-pn-n, all that. Let's say you wanted to be able to just say scan and then the target and have it scan the target. You can use what's known as an alias, and an alias will actually replace the word scan with the full command that you want to run. If you want more complex commands that actually maybe behave differently depending on what flags you add, you can also use functions to do that. So these functions and aliases, they don't get passed on to child processes. So for example, if I spawn a new instance of bin bash like that, then all the aliases and all the functions that were previously in the previous process are not going to be in this new one. So if I wanted to specify any aliases or functions, it makes sense to put them in bashrc, because bashrc gets run every single time that we spawn a new instance of bash. Anyway, you don't necessarily have to understand what profile and bashrc are used for. The most important part is that we have these two files, profile and bashrc, and that they're the system-wide ones and that there are separate ones for each user. The next important concept that we need to cover is signals. Signals are a way of alerting processes to specific events. Basically, they allow us to pause those processes with what they're doing and jump to the operating system or the kernel to run some other things or to do something else. For example, if I say ping 10.0.0.12, this command will run forever. But let's say I want to stop it. How do I go about stopping it? Well, you might be familiar with running Control-C or typing in Control-C to kill a command. But what does that actually do? That sends a signal to that process that is running the command that tells it to stop. So in this case, it's the sig stop signal. So if I say Control-C, it sends that signal to the command, which interrupts it, and then the kernel decides, okay, we're going to kill that process. There are a variety of different signals in Linux. For example, if you use the kill command to kill a specific process, that's the equivalent of using that sig stop signal. If you want to send a different signal, like you want to force kill a process and add -9, that'll use signal number 9, sig kill, that forces the process to terminate immediately. So signals are used in a lot of different places in Linux. However, something interesting that we can do with signals is we can define what happens when a certain signal is received. And the way we can do that is with the trap command. So if I print out the help screen of the trap command, I'm actually going to pipe the output of that into more so I can view it a little more easily. And you'll see here it says, trap signals and other events, defines and activates handlers, or basically commands, to be run when the shell receives a signal or some other condition. In addition to signals, what are these other conditions? Well, these other conditions are mentioned here. Some of them apply specifically to shells like bash. One of these conditions is debug. You can kind of see it as, or view it as, a signal of sorts. That debug gets called every time a command is run. And we can use that to actually run additional commands every time that somebody runs a command. As you can see here, if the signal spec, or the signal, is debug, the argument that we provide will be executed before every command. You might already be thinking about how we can put these concepts together to maybe run a command of our own before anyone else on our machine runs a command. One way we could use that is to log each command to a file. So, for example, let's say somebody runs ls. That's going to send this debug signal of sorts, right? The first thing that's going to happen, this debug signal is going to happen, right? Because we set this trap, then we run any code we want. That code can, if we want to, print out the command that's going to be run to a log file, for example. So it can print ls to some log file, and only then would ls actually get run. Another similar approach that we could use that doesn't involve this trap is using the prompt command environment variable. If you actually take a look at the prompt command environment variable, it gets run every time right before a prompt is displayed. So for example, where we see this user at Debian, right before that was displayed, it ran prompt command. We could also use this prompt command environment variable to run some command of our own every time that somebody else runs a command on our machine. The only very subtle difference between this prompt command and the trap debug method that we talked about earlier is that prompt command will only be run after that person on our machine runs a command. So for example, if I'm to type in ls and I press enter, the first thing that's going to happen is that debug thing, right? It's going to check for if there's a trap there. Then it's going to run ls. Only then would it try to display the prompt again, and before it actually goes about displaying the prompt, it's going to run anything that's in the prompt command environment variable. So prompt command and this trap are two different ways that we can set up logging so that every time an attacker runs a command on our machine, it gets logged to a file. Of course, the attacker could figure this out and override this, but hopefully they're not going to think of looking at the traps that we set up. They're not going to think of looking at that prompt command environment variable, and so we can trick them. I'm not going to show you how to use prompt command in this video because we'll actually be talking about it as a persistence mechanism in the next set of videos. However, I am going to show the trap debug method here. Remember that anything that you can do as a defender, if an attacker gains access to your machine, they can do the same thing. So these methods of running commands or these methods of performing some sort of action every time somebody else runs a command, attackers can also use that to their advantage just as much as you can use it to monitor them.